Welcome all. My name is Suresh. I am lecturer in ECE from Government Polytechnic Belampalli. Today we are going to discuss the next topic is in sixth chapter, that is the last chapter in electronic device and circuits subject of C18 of instrumentation and ECE, both common subject. The subject code is A303C. Quickly moving on to the topic. Today's topic is bootstrap sweep circuit. In the last class, we have seen different sweep circuit, sweep voltage. We have seen the definition of sweep voltage, and we have also seen voltage sweep circuit and current sweep circuit, depending on RC or RL, and we have drawn the waveforms also. How we get the sweep voltage, that is TS and TR restoration time must be 0. Then, if it is 0, then it will become a sawtooth wave or ramp wave. Remember all those things. Okay. Now, quickly moving on to the topic, bootstrap sweep circuit. Draw the bootstrap sweep circuit, that is the topic here. Explain the operation of the figure shows the circuit diagram of a bootstrap voltage sweep circuit. Please, everybody, draw the circuit. One must draw the every circuit, then only you can understand easily and well whenever I explain the operation of the circuit for your exams and remembering also. Please draw the circuit. I can wait 2 minutes. This is bootstrap sweep circuit. After drawing the circuit, please observe the circuit, whether you are familiar with the circuit and type of components, connections, and what can we expect at the output, and what is the operation. As we have already seen from the first chapter of this subject, electronic device and circuits, in the first chapter itself we have seen the basic amplifier with the CE configuration, common emitter configuration. Right? We can remember the circuit looks similar to this common emitter configuration amplifier, but with a little change. There is no input waveform, there is no input signal. Right? We have switch S, which is in its open position. The capacitor is connected between base and emitter, and we have RE, emitter resistance, and the load resistance, and we are taking out across this load resistance, supply voltage VCC, and R1 resistor, R2, and there is a connection of capacitor C1 in between this R1 and R2 to the load resistor, and the transistor is obviously it is a NPN transistor. The ground connection. Make sure you have drawn all the components and label them correctly, and the connection also check once more. I hope everybody has drawn the circuit. Now moving on to the operation. Figure shows the circuit diagram of a bootstrap voltage sweep circuit using emitter follower. Using emitter follower, because emitter follower is a common connector connection. See, it is not common emitter, because we are taking the output across this emitter resistor, sorry, emitter resistor and emitter terminal. We are taking the output across this emitter terminal, and we have made the common as the collector. The collector terminal is common to the input and output. So it is a CC configuration, common collector configuration, and it is also called emitter follower. So using emitter follower as an amplifier, for excellent linearity, the emitter follower gain should be very close to unity, because linearity, from the definition of sweep voltage, the output voltage will be in proportional to the time. That is, in linearity, it should be in linear with the time. That is the first condition to obtain a sweep voltage. So for excellent linearity, the emitter follower gain should be very close to unity. To achieve this, it is necessary to use a transistor with a high value of beta, high value of current gain. To achieve this, it is necessary to use a transistor with a high value of. See the working. Case 1. To explain the operation of the circuit, assume that initially the switch S is closed. Initially the switch S is closed. What happens when switch S is closed? It is in parallel with the capacitor. That is, switch is a short circuit. In the capacitor, there will not be any flow of current to this capacitor. The transistor is in off state. The capacitor C1 is charged to approximately VCC volts via the resistor R1 and RL. Therefore, the voltage across the timing capacitor C is 0. First, we have assumed that the switch is closed. The transistor is in the off state. The capacitor C1 is charged to approximately VCC volts, because when the transistor is in off state, when there is no supply voltage to this transistor, as I is 0, then the VCC is directly applied to C1 through R1. Through R1, the capacitor will fully charge via the resistor R1 and RL. Therefore, the voltage across the timing capacitor C is 0. The C1, right? So VCC through R1 and C1, which is connected to RL and through ground connection. So this will be a closed circuit. This will be a closed circuit from plus VCC, R1, C1, RL to ground connection. As the transistor is in off state, we can open circuit this transistor, and there will not be any flow of this I will be considered as 0 here. When the switch S opens, the capacitor C start charging by the constant current I. When the switch S is open, what happens? There will be another connection will be established here. R1 or C to ground. There will be another circuit will be another closed circuit is also there. VCC R1 or through C and to the ground connection. Then the capacitor C starts charging by constant current I. The rising voltage across capacitor C appears at the base, right? Whenever the C starts to accumulate the voltage, then it will be available across the base terminal of this transistor, which will drive the transistor to on position. The rising voltage across capacitor C appears at the base, and consequently the emitter voltage also increases. Any change in output voltage at emitter is coupled via the feedback capacitor C1 to the point A, such that the voltage VA also rises, because it is all are interconnected, right? When the voltage across this RE increases, which is connected to the RL, and which is a closed circuit via the VCC, R1, C1 and RL, because of this increase voltage here, the VA voltage across this point voltage at point A also increases. such that the voltage VA also rises. Thus, the voltage drop across the current determining resistor R is held constant. See, this is the main point here. Like the voltage drop across the current determining resistor R, current determining resistor which is R, which will be held constant. Though VA increases, because of that, capacitor voltage also increases, which will drive the transistor and which will increase the voltage across the emitter resistor, which will increase the voltage across this load resistor. Then the voltage at point A will change accordingly. Because of this, the I how will be determined I? Because voltage at A minus voltage at B by the resistor. Voltage at A minus voltage at B by resistor. That is VA minus VB by R will be equal to current I. So in order to make the constant current I, voltage difference so the constant current is maintained because of this VA and VB. Next point, in other words, point A in figure will exactly follow point. Means if there is an increase, that means difference will be same. VA increase, VB increase. If VA decrease, VB decrease. Actually, it is if VB increases, VA increases. VB decreases, VA also decreases. This bootstrap action results voltage drop across points A and B constant. Hence current I through resistor R is constant. Because in the voltage switch circuit, if you remember in yesterday's class, that is, if you are using the RC elements in the circuit, right? In the circuits we have R and C. Transistor will act like a switch, and also amplification also. There should be a constant current to be maintained, and the voltage across this capacitor will function as bootstrap. Sorry, it will act as peak voltage. Next point, since this constant current is used to charge the capacitor C, voltage across capacitor increases linearly with time. This peak output is shown in figure 6.17b. In this figure, please draw this figure, all of you. Compulsory draw this figure. I can wait 2 minutes. Mention all these voltages and timings correctly. TS, TG, T, TR. I think all of you have drawn this waveform corresponding literals. Now moving with the explanation. First point, since this constant current is used to charge the capacitor C, voltage across capacitor increases linearly with time. So voltage increases linearly with time. But how much time? Up to where? Because the saturation voltage VCC will limit the voltage note point. It is important to note that voltage across capacitor C1 should not change during the sweep time. For this reason, value of capacitor C1 is kept very large. We have two capacitors in the circuit C, that is C1 and C. The voltage across C1 must be kept constant, and the voltage across capacitor C linearly varies with time because of the constant current, which will be maintained because of VA and VB bootstrap action. Here, observe, we have sweep time, that is TS, in which voltage varies linearly with time. For TS, the voltage reaches to a saturation point, which will remain there up to TG, that is T gate, gating voltage. Then after TG, it will starts decreasing, that is voltage across the capacitor will start discharge through the resistor R, and finally it reaches to its original position in the time TR, restoration time. The capital T is equal to TG plus TR, that is total time. Total time. If we can make TR is equal to 0, then the restoration time is 0. That means the sweep waveform will be similar to ramp. Moving on to the next topic, Miller sweep circuit. Till now we have seen bootstrap circuit. Now we are going to learn about Miller sweep circuit. Please draw the circuit, everyone. Please draw the circuit. I think everybody has drawn the circuit. Now moving on to the explanation. First see the circuit once. There is a triangle shaped component, right? With plus and minus terminals, and in that is written as op amp. Op amp. It is also called operational amplifier. If any of you have heard about this op amp, it is very good. If you do not know what is op amp, you will know in your I think fifth semester you will learn about this component op amp, operational amplifier. Now we have to see only the circuit operation. We don't need to learn about op amp. If you want to know about this component, just read the topic in Google, or you can watch another video. The operation of Miller sweep circuit. Figure shows Miller integrator circuit. See, in this circuit, actually the circuit what will it do, it will act as an integrator circuit. Op amp means operational amplifier. The name comes from the ability of this op amp that it can perform the operations, mathematical operations, addition of two signals, subtraction of two signals, and even multiplication. Then it can do differentiation and integration also. Differentiation and integration. So this particular circuit is an integrator circuit. Consists of resistor, capacitor, op amp, that is amplifier, with a negative gain. Consider the Miller integrator circuit as shown in figure. Step 1. The node B is grounded, right? B is connected to ground. Node A is also at the ground potential from the concept of virtual ground. Yes, there is a concept of virtual ground happens in this op amp, where voltage at VA, voltage at VA and voltage at B, that is VB, will remain same. Should remain equal, then only the op amp will function properly. When both of these inputs are input voltage is same, that means there is no flow of current into the op amp. That is, it will have a very high impedance. Very high impedance the op amp will have. Step 2. As input current of op amp is 0, the entire current I will flow through the resistor R1, also flow through the CF, forward capacitance, shown in the figure. Because why I input is 0? Because of VB. VB is equal to 0 because it is connected to ground, and V also 0 because of virtual ground concept. And I have already told that op amp has very high input impedance, so it will not allow any current to flow through it. But why we need such type of circuits, such type of component? You can just remove it, right? But the application of this op amp will remain in the concept of feedback. The capacitor CF, current flowing to the CF will be available at output, and which is will be feedback through the op-amp. Now see the step 3. From input side we can write I1 is equal to V input minus VA by R1, where we know VA is equal to 0 because of virtual ground concept. So we have Pn by R1. From output side we can write I2 is equal to, see this is from the capacitance formula, current through the capacitance. I2 is equal to C into D difference of D by D of dV by R1, where voltage is equal to VA minus V0. VA is equal to 0, so we have minus CF dV by dt. Equating the two equations 1 and 2, we get V input by R1 is equal to minus CF dV0 by dt. Please write down these equations, then only you can understand the next slide, or remember, write down the last equation itself, only the last equation. V input by R1 is equal to minus CF dV0 by dt. So the step 6 is integrating both sides. We get integral of V in by R1 into dt. The integral is from 0 to t. And minus CF is a constant because it's the component value. It is current capacitance value, which is not a function of time. It is constant, right? We have some numerical value. Integral dV0 by dt into dt. And by mathematical adjustments we got the final equation. V output is equal to minus 1 by R1 CF integral of 0 to t V input dt plus V out at 0 time. That is a initial value concept. If we have some initial value at output and t is equal to 0, if we have V output, it will be available in case of integrals. When we do the integral part, we have initial values. If we don't have any initial value, then it can be taken as 0. Where V output of 0 is the constant of indicating the initial output value. The equation 5 shows the output is minus 1 by R1 CF times the integral of the input. Where R1 CF is called time constant. Time constant R into C of the integral. And the figure 6.19b shows the input and output waveforms for square wave input to the Miller integrator circuit. If you consider that V input is a square wave with certain V minus and V input, V minus input and V plus input, there is a time constant t, time period t, then the integral of this square will be square wave will be a triangular waveform, because if you do step by step integration of these constant values, it is in the square wave we have some positive value and negative value, and there is a pulse connecting this minus and negative and positive values. And the integral of these constants will be some ramps. Integral of these things will be some ramp voltages. And by drawing all the ramps with slopes, some will have positive slope, some will have negative slope, and joining them, we will get a triangular wave. By repeating these waves, we got this perfect triangular wave with some time period, following the time period of square wave. In the node point, the negative sign indicates that there is a phase shift of 180 degrees between input and output. See, right? And we have the V input is in the negative level, but the V output is in positive level. That is the rising. Because of the 180 degrees phase shift between this input and output. The main advantage of such an active integrator is the large time constant. By Miller's theorem, the effective capacitance between input terminals A and the ground becomes Cf into 1 minus AV naught AV, where AV is the gain of the op-amp, which is very large. Due to such large effective capacitance, time constant is very large, and there is a perfect integrator results due to such circuit. For the integration to take, we need to have the time constant should be very large. Then only we will have perfect integration. Right? So these are the important points regarding the Miller sweep circuit. Now the next topic is the applications of voltage and current time based circuits, where we use these time based circuits. As already we have mentioned, to sweep the beam horizontally across the screen in CRO, in television picture tube, in radar, in communication systems, in precise time measurement, and A to D converters, and also digital converters. These are the different problems you can try at your home. Please draw the write down the example. These are the clipper and clamper circuits. We have the topics. These simple problems on clipper and clampers. We are seeing only one or two examples of it now. And this is the last topic in 6th chapter. I think we are going to complete this PDC subject by today itself. So we need to practice some of the other problems also. Still we have 15 to 20 minutes left for this class. So all of you write down the question. First question, draw the output voltage waveforms with the circuit shown if input voltage is square wave of amplitude 5 volts. Assume the ideal diode identifies. See, it is a clearly it is a clipper circuit, and from the tips of this clipper circuit the diode direction PML. N is connected to the upper side, so it is a negative clipper, but we have here instead of the sine wave we have a square wave. So what will happen? Just guess the answer and solve the question by yourself. I will give you 3 minutes. Please think about the question and Yes, and draw the waveforms also. Though it may become wrong, but you have at least tried that one. So you will have different types of solution methods how we can guess the answer, how we can solve this equation. Someone will solve it easily, someone will solve it through the conventional methods, that is long procedures. Someone will quickly guess the outputs in a rough waveform itself. All the things, all the methods may correct, but every method will have its own advantages. In the competitive exams, that is solving the MCQs, then the rough guess itself is enough. Like within 10 seconds or within 5 seconds, within 20 seconds, you can guess the answer. And it is 90% accurate, then you can move on. That will be, yeah. It is in conventional type of question, that is in the exams. You have to draw it by step, then only you can get the 2 marks. Please try it, all of you must try. Before you have just try to solve the question, you have the answer here. Please refer this answer. After the class is over, you refer this video. Now moving on to the next question. Draw the output data on the following clamp circuit. Right? We are going to solve the problem from the concept of clamper. Solution also available in the same slide. Please refer to the first try to solve it by yourself. If you don't get the answer, then see the solution and understand by yourself. Okay, this is a do it yourself type of problems. Now you should solve some of the discussions of clippers and campers. You can go to this website samfoundry.com /online 26 questions answers like that, or you can find many number of questions there, MCQ questions, basic level questions also there. This is just one of the examples that I have made available to you people, so that you can go to these sections and solve the questions, or you can try to do it by itself. Yes, this is a live recording and we are going to solve the basic questions of diode. See, these are the different types of MPQs. You have the answer in the same question itself. If you want to check the answer by yourself, you can check it. First question, see, the abbreviation of PIV in the case of a diode stands for PIV in case of diode. Most of you have known the answer, but see, is it peak inferior voltage, problematic inferior voltage, peak inverse voltage, or peak internal voltage? So most of you have known the answer. It is peak inverse voltage. Of course, it is peak inverse voltage, but where we have seen this peak inverse voltage? PIV, concept of PIV, where we haven't seen this. In the case of rectifiers, I think, right? In order to calculate the efficiency, and in case of reverse bias, the diode should not be get damaged. Otherwise, it will be the circuit, entire circuit will get damaged, and we should replace the diode. The diode should withstand the inverse voltage that we are applying in case of these rectifiers of a full wave and bridge rectifiers. So you can see whether it is right or wrong. So answer C, peak inverse voltage. Not only the answers, the explanation also there. PIV stands for peak inverse voltage. It is the maximum reverse voltage which a diode can bear without breakdown. Now see the next one. What is meant by the PIV rating of a diode? Same PIV rating. Explanation also you can see already that the maximum reverse bias potential which can be applied across the diode without breakdown. So it is the answer A. Now third, the voltage after which the diode current exponential increase with forward bias is not known as please see, it is we have asked that the voltage after which the diode current exponentially increases forward bias. This is the VI characteristics of a diode. In the forward bias condition, you can see this curve will be parallel to the x-axis up to some point, that is up to V gamma, will cutting value. After V gamma, it increases exponential, right? So what is the voltage after which the exponential increases in the forward bias is not known as offset voltage, threshold potential, firing potential, peak forward voltage. See, the answer is peak forward voltage, because offset voltage, threshold potential, and firing potential, these are also referred to V gamma. The voltage after which a diode increases rapidly is known as offset voltage. The voltage after which a diode increases rapidly is known as offset voltage, threshold voltage, firing potential, and cutting voltage, that is V gamma. Beyond this voltage, the forward bias voltage overcomes the potential barrier and rapid conduction occurs. Rapid conduction occurs. See, you have to understand, you have to remember all those extra words. That is, we may call it as, we may have remember it as cutting voltage only. But see, here we have three different terms: offset, threshold, and firing. These already have mentioned in your class, but you may not have remembered. But these type of questions, these are the practical questions we can expect in the competitive exams and in the interview questions also, right? So one must read thoroughly and read entire subject with cautiousness, and what are the important terms, where we have to concentrate more, where we have to understand more. That should be the part of the student work. See, we are the lecturers, we can just inform you that these are the websites available, these are the questions, type of questions you can solve. But it is you, one must solve all those questions. See, there are how many? Only 10 questions in this topic of this website, but there are more than 1000 plus questions, right? 1000 plus questions are also available. So the answer mine. Don't just click on them, but you can move. So these are the different types. So the skipper, voltage character spreader, they from basic to some advanced topics also same. We have discussed all those topics also. Clippers and clampers, diode, clippers, diode, gates, H and transistor bias in hybrid equivalent model, H parameters, characteristics of amplifier. See, all those topics will have. These are the topics which have the MCQs. The available questions are there with the explanation, with answers also there. If you do not know the answer, also you can just click and understand the answer by yourself. Right? So it is up to you guys if you want to practice or not, so that you will be ahead of all those students which are in competition with you. So this is just one website. We have number of websites also. The number of different questions will be available. The explanation with solutions also there. There may be one or two corrections, but most of them have right answers. 98%, 99% will have perfect answers. So not only the concept we teach in these video lessons, only the local author book you have to refer for your end exams. You have to go through the standard books for the concepts, clear-cut explanations, and these type of websites and questions. You quickly revise and quickly think in all the directions. You may have not heard about those words only, words even. Such type of terms also will be encountering such type of questions. So with this, I conclude today's sessions, and it is also end of this chapter 6 chapter, and it is also end of this subject. Even electronics device and circuit subject we have completed in this 20, roughly around 19 to 20 video lessons. And because the students, this is a trial version, the students may not have asked for questions, so we didn't discuss any of those questions also. So it is a quick revision type of videos. If you want to discuss any doubts, please mail me. You know the mail ID suresh@2001 @gmail.com. So thank you one and all. With your permission, I am closing today's session. Thank you. Good night.